Hello and welcome. This is going to be our lecture video for April 3rd. Going to be talking about a little bit more on graphing and reciprocal trig. So our do now asks us to write the equation of a sine wave that's been vertically shifted to go through the point 3 pi over 2 comma negative 8. If you haven't already, get your notes out. Here we go. So we should basically have the very rough features of a sine wave memorized. We should know, for example, that a sine wave starts at its midpoint and then starts going up. All right, it hits its peak at pi over 2. It comes back to the midline at pi. It hits a trough or a minimum at 3 pi over 2. It's kind of an important one to remember. And then it comes back to the midline, completing a full cycle at 2 pi. We should have this basically memorized for a sine wave, because if you know these 5 key points, we can start shifting them other places on the graph, depending on what sort of transformations we want to do. So let's see, at 3 pi over 2, our unshifted graph, I'm going to add this point in, 3 pi over 2 is at its minimum, and the amplitude is just 1 if we don't see anything there, so it must be at -1. We want to shift this down so that it hits -8, so that gives us the equation y equals sine of x minus 7. That way it takes this point that was at -1 and moves it down to -8. Everything's going to get shifted down here. Okay. Goal for today is to understand all of the transformations possible on a trig graph and to understand the ratios represented by reciprocal trig functions. Why reciprocal trig allows us to use the exact ratio you want in a triangle. You're not restricted to just SOHCAHTOA. You've got 3 more options for how you can turn those side lengths into ratios. Also, if you're trying to fit some very unique data, you might want to use one of our reciprocal trig graphs because they make really interesting curves that might fit some very specific data that you run across. All right, we've seen this before. Let's just review it real quick. Standard form of a trig graph, we know A is amplitude, K is vertical shift, and then B and H combine to make 2 things. One is phase shift, which is sort of like horizontal shift. We call it phase shift because these functions are periodic, and one type of shift might be the exact same as another horizontal shift. We're going to see that later on. But phase shift is always h over b. You flip the sign that you see on h because the minus is already built in. And then period is always 2 pi over b, at least for sine and cosine. If this was tangent, then it's just pi over b, because tangent has a period of pi. One way to help you remember this is that b is always on the bottom. B is the second letter of the alphabet, so it should be in the second spot, however you want to remember it. Okay, so let's try and graph a trig function by hand, so no help of the calculator here. This one is a cosine wave. So cosine is another one that we need to have the basic features memorized. So sine started at a midpoint, cosine starts at a maximum. It starts up here at 1, and then at pi over 2 it goes back to the minimum. At pi it hits, or goes back to the midline. At pi it hits its minimum. 3 pi over 2 back to the midline. 2 pi it's back up to its maximum. So that's where this graph is right now. Let's now apply the transformations to it. So I'm going to pick some lighter colors to try and, no, it's not that light. Keep track of this graph. So in orange there, I've just graphed y equals cosine of theta. Let's see what happens after I apply the amplitude shift. Y equals 4 cosine theta. All of these points are going to get 4 times higher off the midline, but still have that same midpoint. Okay, let's apply the vertical shift next. Y equals 4 cosine theta plus 1. So I'm going to move every point up 1. So now our wave is up here. All right, period is the next one. I'm just going to write what the formula for period is. This one's kind of tricky to graph. So 2 pi over b. Our b value is 2 here, so it becomes 2 pi over 2 becomes pi. So instead of doing one full wave every 2 pi, now it's going to do a full wave every pi. That doesn't change our starting value. We're still going to start right here at 5, but we're going to come back to the maximum after just pi. And so then I can split that in half to find where we're going to be at our minimum at pi over 2. And then at these fourth units, we'll hit our midlines. Okay, so that gives us one cycle, but now we've got room over here now that's been kind of scrunched in to get another full cycle. And it's going to complete another full cycle by 2 pi. All right, it hits right there at 5 pi over 4 and 7 pi over 4. Okay, and now we got to do the phase shift, and that'll be our last thing. So the phase is h over b equals 7 pi over 4 all over 2. Notice I left the minus behind. I just brought the 7 pi over 4. And then this 2 can swing up and multiply this 4 because it's copy dot flopping. And this gets 7 pi over 8. And that is because it's positive, it's 7 pi over 8 to the right. What that translates to on this graph, if 4 boxes is pi, then it's 3.5 boxes to get 7 pi over 8. So every one of these points needs to move over 7 pi over 8. But when I moved the maximum, it ended up just a half unit away from this other maximum. So you can make your life easier by, instead of moving all of these points 3.5 boxes this way, move all of these points just a half box this way. And I think I'm doing this in green. And so that's one of the useful features of phase shift, is if you do it last like this, you can see, was there a shorter way to accomplish the same shift? Moving 3.5 boxes one way is the same as moving just a half box the other way. And here in green is my final graph. I know it's kind of messy because there's so many transformations there. But we'll just say green. Okay. These are tricky. I won't have you do a whole one of these on any assessment, but just talk about the specific transformations. And then you can use your calculator for pretty much everything else. Let's see, it's coming back down. There we go. All right. So the extra practice link on the calendar for today, I think this one's really good. I want to show you how it works. There we go. I really think you should practice this one because you can get some good graphing practice without having to do as many annoying steps as I just showed. Okay, so this one here wants us to graph -4 cosine of x plus 3. So we can slide these things around. You just, with these 2 points, a midpoint and either a minimum or a maximum, whichever side you want to drag it to, you can get any wave that you want. So I know cosine normally looks like this. It starts at a maximum and it cycles every 2 pi. But this thing now has an amplitude of -4. So I'm going to drag its maximum down to -4. So it's down 4 off the midline. Now I see this plus 3. That means everything's going to be vertically shifted up 3, including this point here, 1, 2, 3. And looks like I did it right. Let's try one more because this one's got a period change. So it's a cosine. So again, I want to start with my maximum right on the y-axis. Let's see, amplitude of -2. It's been vertically shifted down 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then the period has been changed too because we got this b value. So now I've got to do 2 pi over 1/6. And that becomes a 12 pi. But the 2 points they give me are only 1/4 of a way through a full rotation. So I want to drag this over 3 pi so that it will complete a full cycle by 12 pi. Let's see if I did it right. There we go. Let's see. Oh, no, it's not giving me a sine one. But if you do get a sine one, you want to start more like it is now with the midpoint right along the y-axis. Okay. Put this away. Okay, let's see if we can get through a little bit more. Equivalent functions. I think I can keep this just one video. So can we come up with a list of equivalent functions that have the same graph as y equals sine of x? So let's just remind ourselves what the graph of y equals sine of x looks like. Starts at a midpoint, goes up from there, returns back to the midpoint at 2 pi. Well, one thing I could do is if I shifted this a full 2 pi and did y equals sine of x plus 2 pi, well then every trough is going to just move over to cover the one next to it. Every peak is going to move over to cover the one next to it. And these are going to be equivalent functions. All right, I can write a few more. Y equals the sine of x plus 4 pi. Moves everything left 4 pi units. Again, everything would just cover right back up. Now how I can write this in a way to get all of them is I say y equals sine of x plus 2n pi. 2n pi, where n is any integer. All right, there's a way to do it with cosine as well. All right, cosine normally starts at a peak and then comes back to a peak every 2 pi. Well, I can shift my cosine wave to cover my sine wave if I just move everything pi over 2 units to the right. So another graph that's equivalent to y equals sine of x would be y equals cosine of x minus pi over 2. And that's going to shift every peak over to cover exactly what a sine wave looks like. I could also move a full 2 pi plus a pi over 2, and that would be, let's see, 2 pi is 4 pi over 2, so that would be 5 pi over 2, so minus 5 pi over 2. Y equals cosine, I can move a whole 4 pi, which would be 8 pi over 2 plus an additional pi over 2 is 9 pi over 2. All right, now this one's a little bit more tricky to write just algebraically, but it's x minus, let's see, I want to do one more than multiples of 4, so 4n plus 1 pi over 2. Okay. We're actually going to save more problems like this for our next unit, where every time we answer, we want to answer in a way that gives us all of our answers like this. And being any integer applies to this one as well. All right. Our next slide asks us to write all functions that would be equivalent to this function here. Let's just make that all sine functions. It's pretty tricky to think about how to get a cosine wave to cover a sine wave that has so many transformations. But if we keep it as a sine wave, there's actually just a real easy trick we can do. And that is, we can always just copy the function exactly and then just say plus 2 pi n inside the parentheses here. And this is going to give us all of our equivalent functions. Here, let's write this as gives all equivalent sine waves. All right, and you might think, well, do I have to account for this too? Well, it does change the problem. It makes this wave cycle a little bit more frequently than a normal sine wave. So this one's cycling pretty frequently. But because B appears in the formula for phase shift 2, it cancels out the fact that it changes the period. And it means that we can always just do a plus 2 pi n here. And somewhere you want to always say that n is any integer. Okay, so I know like these last two slides were pretty tricky, but if we could just remember one thing, it's that you can always get an equivalent function by just wedging in a plus 2 pi n inside the parentheses of your sine wave. All right, on to reciprocal trig. So let's start with our right triangle. All right, if you know it's a right triangle and you know one of the angles that we call theta, then you really know all three angles because of the interior sum of a triangle formula. And then once you know all three angles, we can say all of these triangles are similar and therefore the ratios of their side lengths must be the same regardless of how big or small we draw this triangle. All right, the side opposite of our reference angle theta, we call opposite. The side next to it that isn't the longest one, we call the adjacent, and then the longest one we call the hypotenuse. Okay, that should all be a review. All right, normal trig enables us to take in that angle and gives us the following ratios in any triangle right triangle that has that angle. Sine always gives us opposite over hypotenuse. Cosine always gives us adjacent over hypotenuse. And tangent always gives us opposite over adjacent. Okay, that's all review. But given these three ratios, there's three more ways that we can combine them. We can flip these all over. And so if I wanted to flip over the ratio, you flip over the trig function by doing 1 over that trig function. So 1 over sine of theta gives us hypotenuse over opposite. 1 over cosine of theta gives us this ratio flipped over, hypotenuse over adjacent. And 1 over tangent of theta gives us adjacent over opposite. All right, now these get their own special words. So 1 over sine, this is called cosecant, and it gets abbreviated CSC of theta. 1 over cosine, this gets called secant, and it gets abbreviated SEC. And 1 over tangent, this is the only one that actually makes any sense, is called cotangent. All right, it really confuses me often that the reciprocal of sine is cosecant and the reciprocal of cosine is secant. I just remember that it's backwards of what I think it should be. And then that honestly helps me remember it more than any other mnemonic I've learned. It's just that these two are backwards. And yeah, sine leads to cosecant, cosine leads to secant when you invert them. So now that we know these, if I really want to get hypotenuse over opposite, I'm not happy with opposite over hypotenuse, I can use cosecant. You don't have a cosecant button on your calculator, you have to plug it in like this, 1 over sine. All right, so this is how you plug it into your calculator. All right, one last thing. Let's look at the graph of y equals secant of x. So I'm gonna get out my graphing calculator, and what I'm gonna plug in is 1 over cosine of x, and we're gonna take a look at that graph. All right, so I go to y equals, and I'm going to do 1 over cosine of x. All right, now I got to pick a good window. Well, your window is going to depend on what mode you're in. I'm in radian mode. So I'm going to go from, for my x values, I want to go from negative, let's go 2 pi to 2 pi with tick marks every pi over 4. For my y scale, negative 6 to 6 seems fine. Let's take a look at the graph of secant. So yeah, very interesting shape to this one. Not like anything we've ever seen before. I'm going to try and sketch it onto this graph here to show how it relates to cosine. So secant starts at 1, but then it has an asymptote at pi over 2. And that makes sense. Secant is 1 over cosine, and cosine is equal to 0 at pi over 2. So when cosine is 0, secant is undefined. So we're going to have asymptotes at pi over 2, 3 pi over 2, everywhere that cosine is equal to 0. Or you could think of it as secant is hypotenuse over adjacent, so it's at every angle that leads to the adjacent being 0. Okay, so at pi over 4, let's think about that one for a second. That'd be adjacent over hypotenuse would be the square root of 2 over 2. That would be 2 over the square root of 2, hypotenuse over adjacent. So 2 divided by square root of 2 is 1.4. So right about there, and then it goes off the graph. Not very good. All right, it goes up to positive infinity, disappears, reappears at negative infinity. It's going to hit negative 1 at pi. Let's add in those negative 1.4s. That was looking good. Disappears, reappears back to 1 at 2 pi. All right. And now if I just added in cosine, you're going to see a relationship here. Cosine goes like this. It keeps hitting our secant wave right at its maximum and minimums. And then when it crosses 0, so the section's not very good, it should be crossing 0, then secant has that asymptote. Okay, so orange is secant, red is cosecant. All right, let's call it good for this video. Have a good rest of your